Good morning. We're going to start the second day with just another example of a confidence interval. This time we're going to go with a 90% confidence interval, so we have to have a different Z star. We have a San Diego reproductive clinic who had 49 live births to 207 women. So that's a sample proportion, so that's a p hat. So 49 out of 207. Under the age of 40, we don't really care about that 40, who had previously been unable to conceive. We want a 90% confidence interval for the success rate of the clinic and interpret the interval in context. Now, this is new. Assume that conditions for inference have been met. We love to hear those words because when we see those, it means somebody has already checked the random, the 10% condition, independence, if we have PQs and P hats are at least 10. So we don't have to redo it, which means we can skip straight to knowing that a normal model will work and writing our confidence interval. So for confidence interval, we start with a P hat, which is 49 out of 207. This makes a not so friendly decimal, so I'm just going to keep it in fraction form. Plus or minus, and we need a Z star for 90%. So what does that mean? If we have a normal model and we want to capture the middle 90%, we want to know the Z-scores associated with each end of that. So we could do an inverse normal, and normally I'm looking for this positive upper Z-score, but they're opposites, so either one will work. So if 90% is in the middle and 10% is in the tails, that means 5% is in this lower tail and 5% is in this upper tail. So there's 95% of all possible samples that lives below this Z star right here. So using the inverse normal command in the calculator, if we ask for the inverse normal with an area of 95% or 0.95, we're going to get Z star equals about 1.64. So substitute that in, 1.64 times the standard error. And because I'm using a fraction this time, I'm just going to have to subtract 49 from 207 to get my failures. So 49 out of 207 successes. And if we subtract 49, we get 158 failures out of 207. And then divide that P hat times Q hat by the sample size, which is 207. And then we want to crunch that out in the calculator. So I would do the subtraction, then I'd do the addition, and get my lower and upper bounds. And normally I'm going to use interval notation just because it's quick and easy and I don't have to worry about writing my parameter down. So if I do the subtraction and crunch all that out, I'm going to get about 0.188. And if I add, I'm going to get about 0.285. And then I need to interpret. So write the interpretation of the interval in context. So we are 90% confident that between 18.8% and 28.5% of, all right, let's get our context, women under the age of 40 will successfully conceive with the help of this clinic. So remember that interpretation is about making a prediction about the population of all women. I really probably should stick the word all right there. All women under the age of 40. So we're making a prediction about what's going to happen in the entire population based on what we saw in this one sample. Would it be misleading for the clinic to advertise a 25% success rate and explain? Well, is 25% between 18.8% and 28.5%? Yes, it is. So anything within that window is a legitimate claim. So would it be misleading? No, because 25% is in the confidence interval we constructed. Okay. Now, more questions. The clinic wants to cut the stated margin of error in half. How many patients must be used? Okay, so I'm going to kind of go with this backwards, and then I'll convince you. So, what if we made the number of patients 4 times as big? So let's just have a little algebra adventure here. Okay, so margin of error is z star times the square root of p hat q hat over n. So that's the formula for margin of error. I'm trying to cut it in half. So if the left side needs to be half as big, the right side needs to be half as big to keep the two sides equal. Well, let's just play with some numbers. If I quadruple my sample size, so 4 times the old sample size n, okay, what's the square root of 4? 2. We got an understood 1 in front of the p hat q hats, just thinking of the algebra, so there's a 1/4 under that square root. And the square root of 1/4 is, square root of 1 is 1, square root of 4 is 2, so it's 1/2. So I could pull out a 1/2 if I take the square root. And then just rearrange my factors, pull the 1/2 to the front. So 1/2 times z star times the square root of p hat q hat over n. Now this was my original formula, okay? If I end up with this, the z star times p hat q hat over n is what I originally had. And that was equal to margin of error, but now that I'm multiplying that right side by half, that means I have to multiply the left side by half. So I get half the margin of error by quadrupling my sample size. In general, to get a margin of error 1 over, let's just pick a constant, a, as large, we need to increase the sample size by a squared. Okay. In this case, we want it half as big, so that's 2 squared, which is 4 times as big. So my new sample in this particular context needs to be 4 times as big as the old sample. The old sample size was 207. And then 4 times 207 is 828. Okay. So I need 828 patients to cut my margin of error in half. What might be a potential problem with the sample size found above? This is not a single right answer, but all of our inference procedures are based on meeting conditions. And so it could be that 828 patients is a fairly large number, particularly for 1998. So 828 maybe, we don't know for sure, we're just speculating, maybe more than 10% of women who visit this clinic who are over the age of 40 and have had previous trouble conceiving. So it could be a sample size too big issue. And anytime you see a problem like this, really it wants you to kind of go back and recheck conditions. It could be sometimes an issue of independence. So we're just going to try to throw out something reasonable when we're asked that sort of a question. Okay, next page. A poll of 1,505 likely voters indicated that 52% would vote in favor of a proposed constitutional amendment. So N is 1,505, P hat is 0.52. A report on the poll said that the margin of error for this poll was 3%. What level of confidence did the polls use? So level of confidence is associated with the Z-star. Z-star tells us whether we have 90%, 95%, 98% confidence. So our first task is going to be to find Z-star. So I'm going to need an equation to solve. The margin of error equation has all the pieces in it that I need. I know that the margin of error equals Z-star times the square root of P hat, Q hat over N. If I substitute in everything that I know, margin of error was 3%, so 0.03. Z-star I need. P hat was 0.52, so Q hat would be 1 minus that, or 0.48 over the sample size of 1,505. I'm going to save us the number crunching time today because you can crunch numbers on your own. To solve for Z-star, we would need to divide both sides by the square root of all that mess, so 0.03 divided by all that mess, which turns out to be 2.33-ish. Okay, and I need to know what percentage under the curve that is, what level of confidence. So if I think about normal curves, and I have a Z-star of 2.33, which means the lower boundary is negative 2.33, I want to know what percent of stuff is in there. So if I run my normal CDF command and use negative 2.33 as my lower bound, positive 2.33 as my upper bound, and do normal CDF, it's going to spit out a percentage between those two cut scores. And it turns out it rounds up to 98% if you round it off to the nearest whole number of percentages. So we have 98% confidence. One last question about this one. Why might the poll actually be inconclusive? Well, let's look at the actual confidence interval. Okay, the P hat was 52% with a margin of error of 3%, which means we could be as far off as 3% from the center, or 98% confident that we are. So we could go 3% below 52%, which is 49%. And the higher end, the upper bound is 3% more than 52%, which is 0.55. So this is the actual confidence interval based on the information given up here. 50% lies in there. As a matter of fact, 49% is below half, 55% is above half. So since the interval contains values below and above 50%, the amendment could pass or fail to pass. Could go either way. If our entire interval was above 50%, then we would conclude with 98% confidence that it's going to pass. But since we're straddling 50% with that interval, it could potentially go either way. Okay, we've got 2 more slides. I don't have time on this video to do it, so I'm going to stop it, and then we'll pick up those last 2 slides on the second video.